Hi, everyone. So this is just a quick discussion about one of the other ways that you can stress a reaction system, or rather an equilibrium reaction system. Today I talked about one of those methods, which is changing concentrations, and then the reaction will shift in response to that. The other way you can stress a system is by changing the temperature. And there's this one is a little bit more confusing in the sense that it depends, and it's not 100%, but there is a general trend here. The general trend is that if a reaction is endothermic and you increase the temperature, that has a tendency to shift the equilibrium towards the products. So it shifts to the right. If the reaction is exothermic, increasing the temperature tends to shift the reaction back towards the reactants. And then the inverse is also true. If instead of increasing the temperature, you decrease the temperature, and it's exothermic, and it's endothermic, it's going to be left. If it's exothermic, it's going to shift it right. So I want to give people a real example of this. So let me just pause this video, and I'll show you a real example of that.
Okay, so this is actually an example of one of my favorite. I don't know why I enjoy this particular example so much, but this is an example of one of my favorite equilibrium reactions, which is a reaction of nitrogen dioxide. Two nitrogen dioxides combine to make dinitrogen tetroxide. Nitrogen dioxide is actually this ugly brown gas. So this is nitrogen dioxide, and there's a solution of it as well down here. N2O4, on the other hand, is a colorless gas. And so what you observe here is that as I change the temperature of this system, as I cool it down, the gas tends to go from mostly brown, lighter brown, until it's essentially nearly colorless. And that basically says that, okay, as you cool down the gas, the reaction shifts towards the products. So based on that observation, let's see if we can predict using our general rules whether this reaction is exothermic or endothermic. And since in this case, let's see here, as we've decreased the temperature, so that's going to be the left column, the right-hand column there. As we decrease the temperature, the reaction was shifted towards the right-hand side, towards the products, which was the colorless gas. So that implies that this is actually an exothermic process. So one reason why I like this particular example is that this is a process, this is a gas that you guys are, if you're not familiar with it yet, you will become more familiar during your stay at LMU, and rather just your stay in LA, which is that nitrogen dioxide, that brown color gas, is one of the primary components of photochemical smog. So it's what gives that brown hazy color. There's a few other components to smog, but all the nitrogen oxide compounds tend to be brown, especially nitrogen dioxide. And if you've been been in LA over the summer, what you may have noticed is that the color of the sky is a little bit darker. It's a little bit photochemical smog is a little bit worse during the summer months than it is during the winter and spring months. And there's a few reasons why. Partly it has to do with just the amount of people on the roads changes, prevailing winds, and other causes. But one reason why the sky looks a little bit worse is that higher temperatures skews this reaction back towards the reactants. And you actually have more NO2 present, meaning the sky looks a little bit browner.
Okay, so I admit the board is a little messy now, but bear with me here. So this was the reaction that I was just showing to you guys, and I asserted to you that it was an exothermic reaction based upon applying our understanding of how equilibrium systems change with temperature. We were able to identify it as an exothermic process. Now, fundamental question, why is it an exothermic process? The reason why it's an exothermic process is the reaction that occurs here is you take NO2, which is a radical, it has an odd number of electrons, so the nitrogen has an unpaired electron, and so does the other nitrogen dioxide molecule. When they react, they come together and they form a bond between them. And forming bonds is an energy lowering process, so forming bonds is an exothermic process. So this is an exothermic process. But how can we rationalize, okay, why is it that changing the temperature shifts the equilibrium in the forward, or for that matter, in the reverse direction? Why does it shift it into the forward reaction? So keep in mind that the equilibrium constant for this reaction, we defined it first. We said that the equilibrium constant, the law of mass action, tells us that the equilibrium constant is related to their partial pressures. But when I first started talking about equilibrium, I asserted that it's actually also related to the relative values of the forward reaction and the reverse reaction. And so what ends up happening here is, depending on the nature of those forward and reverse reactions, well, those forward and reverse reaction rates are also temperature dependent. We use Arrhenius theory to logic to ourselves, or try to give a justification. We use Arrhenius theory and collision theory to sort of explain why does a reaction rate increase with temperature. That, oh, there's this activation barrier, this activation energy that you need to supply for the reaction to go forward. So this is a reaction profile for a reaction like this. It's exothermic. There ends up being a net drop in energy. The forward reaction has an activation energy. It's the energy you need to go from here over this hill. So there's an forward activation energy. And there's also a backwards activation energy now. There's an activation energy from going from the products. You have to go over the same hill back to the reactants. But in this case, the backwards activation energy is larger than the forward activation energy. And that's important in terms of predicting how the rates of these reactions increases differently with time. So if we recall the form of the Arrhenius equation, the form of the Arrhenius equation says that the rate constant is equal to, or it's proportional, I'll just say it's proportional to e to the minus activation energy over RT. So if you take the natural log of this, and you take the natural log of the E, and you plot it versus 1 over the temperature, you get a straight line, where the straight line is the activation energy over the gas constant. So this is me plotting the slopes and plotting the Arrhenius equation for these two different reactions. I asserted here that, okay, the forward reaction has a small rate constant, so it should have a relatively small slope, or slope is small in magnitude. The backwards reaction has a relatively large activation energy, so it should have a much steeper slope. So now the question is, okay, if I change the temperature, that's going to change the forward rate, and it's going to change the reverse rate. But relative to each other, how do they change? In this case, because the backwards reaction has a much higher activation energy, it has a steeper slope. And so its rate constant speeds up more as you increase the temperature. Or conversely, it slows down more when you lower the temperature. So if I increase the temperature, so I make temperature higher, that's meaning going actually further on the left on this scale. So it's a little wonky because I'm plotting 1 over the temperature. So a high temperature corresponds to a low value of 1 over the temperature. If I raise the temperature, okay, so for instance, like at one point, if I raise the temperature a little bit, the backwards reaction rate increases faster than the forward rate does. So again, this guy, they both increase. The forward rate increases, but the backwards rate increases more. And as a result, the equilibrium constant is shifted. It's oh, did I have that backwards? Yeah. Yeah, I have that right. That's right. So if the backwards rate is faster than the forward rate, that means that the equilibrium shifts to the left. It goes in the direction of that backwards reaction, and you start producing more products again. And that's the fundamental reason why reaction, or how to explain this general observation. If I had an endothermic process, so an endothermic process would look like this. And then now, in this case, I'll keep the colors the same here. In this case, now the backwards, or rather the forward, that's the forward activation energy, and this here is that's the backwards activation energy. Now the backwards activation energy is smaller, and so I would expect these curves to flip places, and that means that basically, as I raise the temperature, the forward reaction rate increases more quickly than the backwards reaction rate does. If it's an endothermic process and I increase the temperature, the forward rate speeds up more than the backwards rate. So that's why in an endothermic process, if you increase the temperature, the reaction shifts right. That's the fundamental reason why these guys have different responses to temperature. And I do want to give you guys that explanation because it sets up a fundamental point here, which is that equilibrium constants are temperature dependent. So this is a fundamentally different process or different way to conceptualize how the system shifts than when we're looking at concentrations. You can change concentrations, but the equilibrium constant doesn't change. That's why we'll often say the equilibrium concentrations don't determine the equilibrium constant. It's the other way around. Concentrations don't determine equilibrium constants. The equilibrium constant determines the concentrations. Concentrations can change, but the equilibrium constant is constant. But it's only constant at a constant temperature. The equilibrium constant can change, but only if you change the temperature. Then, because you change the temperature, you change the equilibrium constant, and that causes your subsequent concentrations or partial pressures to change as a result, or change accordingly. So that's the fundamental, deeper reason to explain this pattern. Your textbook gives you another possible explanation, which I'll refer to as a bullshit explanation, because it is bullshit, and I'll tell you why it's bullshit. But I'll give it to you because it does feel a little bit more instinctive, but it's an instinct that is it will work in the sense that you'll get the right answer, and in that sense, it's not bad knowing it. But instinctively, it's an incorrect rationale. But I will give it to you anyway, just because it's good to have a couple of tools in your pocket. The way to think about this is, okay, this is an exothermic process. So we can think of heat as a product. It's an exothermic process. It releases heat. It generates heat. So we can think of heat as a product here. And if I increase the temperature, well, that's kind of like increasing the amount of heat present in the system. And as a result, okay, I increase the concentration, quote unquote, of one of my products, so the reaction shifts to the left. And that matches up with this general observation that for an exothermic reaction, which this is, if I increase the temperature, the reaction shifts left. Now, I don't like that explanation, and it's not an explanation. It's a quick and dirty way to remind yourself of this pattern. It's not correct for two reasons. One, heat is not the same as temperature. You can't say increasing the temperature is like increasing heat. Heat and temperature are completely different concepts. Heat is a transfer of thermal energy. Temperature is the measure of the average amount of thermal energy in a system. So heat is referring to a process. Temperature is an actual parameter for a system. So in that sense, it doesn't make sense. The other reason why it doesn't make sense is that if you have only this picture, you're losing this other important point, which is that changing the temperature fundamentally changes the equilibrium constant. We'll talk more about the temperature dependence of equilibrium constants when we get to chemical thermodynamics, and we'll be able to come up with an expression that relates the energy change for a reaction to the equilibrium constant. And then when we do that, that will be explicitly temperature dependent, and we can justify this a little bit more. But generally speaking, this is an alternate way to think about or rationalize to yourself how a process can respond to temperature. So I'll give you an example of something that's similar. And again, this is not the best example, but it's one I will use. Something like this, the dissolution NaCl into water. If we recall from the demonstration I did, this made the solution cool down, and so that was an endothermic process. So you can think of heat as being a reactant in that process. You require energy because it's endothermic. Energy needs to go into the system, needs to be supplied for this to occur. And how does the solubility of sodium chloride vary with temperature? Sodium chloride's solubility, the solubility of most salts, tends to increase with temperature, meaning that as I increase the temperature, as I add more heat, the reaction shifts right towards the products, meaning I drive more of the sodium chloride into solution. That's a hand-wavy explanation, but it's not a terrible explanation. So that's just a very quick rundown of the temperature dependencies of equilibrium systems. They change with temperature, and how they change with temperature depends on whether they're endothermic or exothermic. I just want to wrap up and say that this is a general rule. Usually this is the case. There are exceptions. Like for instance, lithium chloride is has an exothermic heat of solvation. When you dissolve lithium chloride, that produces heat. But the solubility of lithium chloride actually increases with temperature. So it doesn't follow the same rule here. So there are exceptions to this, but that's the general rule of thumb. Okay, so that's it for this video. If you have any questions about it, please shoot me an email, stop by during office hours. I'm going to have a quick question about this at the beginning of lecture on Monday to sort of test people's understanding of this. So we'll discuss this more. All right, have a good weekend.